Let's go. What is a redox reaction? Electrons are moving in between atoms. Reduction means gain of electrons. Oxidation means. How do you feel about these vocabulary words?
Good. Not good.
Not good.
I don't like them. I'm gonna be honest. I'm kind of a hater.
Why do you need the homework to be
Also,
What?
Leo the lion says
Just in case.
grr. How do you
Also,
forget that?
Leo the lion says grr.
Yeah, I was
I like Leo the lion says grr.
Or you could just
Oxidation reduction reaction is a reaction in which electrons move from one atom to another. The reduction means gain of electrons. Oxidation means loss of electrons. I already heard Leo the lion says grr. What's another way you could choose to remember it? Oil rig. Oil oxidation is lost. Rig reduction is gain. Did anybody else write a different thing for question 4?
Electrons are gained, so the charge is reduced.
Yeah, if electrons are gained, they're negative, so the charge is reduced. I wrote all 3 in the key. Random side question. Why is this not a real chemical reaction? Yeah. You're never going to find pure chlorine on its own like that, so this is an intentionally oversimplified reaction, but it does what we need to do. Why is this a redox reaction?
Steals.
Yeah, if we go back to when we first introduced covalent, ionic, and metallic, ionic, the strong nonmetal steals an electron from the metal. Stealing an electron is another way to describe an electron moves from one to the other. When an electron moves, that's called redox. Which one is being oxidized?
Sodium.
Oil, oxidation is lost. Since sodium lost it, it was oxidized. And rig, reduction is gain. Since chlorine gained it, it is reduced. The half reactions. Why do I have to add electrons instead of subtracting them?
Because you can't subtract. Yeah.
Yeah, so chemistry is not exactly math. Chemical equations are recipes. And so if you have a recipe, you're never going to be like, add some cookies and remove the sugar. Like, the sugar doesn't stop existing. And so one way you can think about it is, before I have chlorine and an electron, afterwards they're stuck together, so the chlorine has a negative charge. Or before I have some pure sodium, after I have removed an electron so that the sodium is positive, but that electron still exists. It just exists no longer attached to the sodium. And then number 7, oxidation and reduction always happen at the same time. This is true for the same reason as, here's a pop quiz. All right, did I just turn away from you or towards the screen? Both. I can't do one without having done the other. You can't have oxidation without having reduction. No, just my light bulbs are weird. And we may have damaged them. Number 8, is the following reaction a redox reaction? No. There is no electron transfer. So, potassium has a positive charge because it's missing an electron. Chlorine has a negative charge because it has an extra electron. Is potassium chloride covalent or ionic? It is ionic because it's a positive, or because it's a metal and a nonmetal. Ionic means it's made out of ions, which means my positively charged potassium happens to be sticking to my negatively charged chlorine. Because it's positively charged potassium both before and after, I didn't do anything to its electrons. There was no electron transfer. Realistically, this isn't even a chemical reaction at all. The real life scenario that this equation fits would be something like, if I have potassium and chloride dissolved in water, they're technically not touching each other. But if I boil the water off, they will start touching each other. And you had potassium chloride dissolved, and afterwards it was solid, but it was potassium chloride the whole time. So this is not only not redox, it's also not a chemical reaction. The funny thing about this is I did this on purpose. The link that I sent you,
That's what I'm doing.
the link that I sent you was not a link to a video, it was a link to a playlist, because Redox can get a little bit overwhelming at the beginning. And so while we're not going to cover everything that Tyler DeWitt covers, he covers everything that I'm going to cover. And so just like going through some of his videos, if you get stuck, it looks like his battery stuff isn't in this playlist, so you'd have to like search for that. But if you let this video play until the very next one, we're probably going to have an ad. Grammarly.
And welcome back to this U.S. Open office plan.
Miller just lobbed a message way over Jones's.
Here's an example.
This is the very next video in his list.
Your face. Oh, it's the same as your face.
It's just number 8 on the homework. You guys are fun.
No, you're suck. I would not be asking you for that. Yeah, you
What? I would give you a great recommendation. I'd be like, oh, you changed your mind?
No, I was thinking about that. I was like, I want Mr. Right.
What?
Yes. Then it has an N.
All right.
It's gonna say letter N and then they go. That's what I was
Yeah.
And then I would end with thing could stop her from being an excellent ambassador. Nothing could stop.
I thought you were saying like something.
No, nothing. You said no. I finished it. All right. We need to jump into the notes. We have exactly 2 skills that we need to master today, and they look weird compared to things that we've done in the past. What is the full definition of an oxidation reduction reaction? It is a reaction in which electrons are transferred between species. The reason we use the word species is it's basically a catch-all word to describe all the different kinds of particles. So sometimes they're transferred from one atom to another. Sometimes they're transferred from one ion to another. Sometimes they're transferred from a molecule to a different molecule. So we don't want to have a definition that doesn't allow for one of those things. So effectively, if an electron moves from one thingy to another thingy, it's a redox reaction. Because I'm a scientist and we have to use cool words like species. I wanted to put the mnemonics in these notes so that they were all collected in one nice place. One thing that's really, really important about these mnemonics, though, is the word electrons. So Leo says Gur, it's already built in. Leo, loss of electrons is oxidation. Gur, gain of electrons is reduction. But oil rig, you just say oxidation is loss. It's really, really, really important that you recognize oxidation is loss of electrons. So if, for instance, you were talking about charge, oxidation is not loss of charge. Reduction is loss of charge, right? And so remember that these are designed to tell you what electrons are doing. And we're not always exclusively talking about electrons when we talk about oxidation state, or when we talk about redox reactions. So just remember, if you're using these, have the words of electrons somewhere in your mind so that it sticks. I like history at least a little bit, and I think it's fun to know why things have terrible names. So anytime in chemistry something has a name that just doesn't make logical sense, the reason that name exists is almost always because the guy who discovered it and named it had no idea what was actually happening, and then everybody called it that for decades or centuries until we finally figured out what was going on, but it's too late. It has a name, it's already written in all the books, so we don't change the name. The classic example is the word atom. If you remember, the word atom is the Greek word for indivisible, and yet redox reactions is all about dividing electrons out of them and doing stuff with them, which is like wildly easy. It's not even hard to divide an atom. Atoms are so super divisible, so it's a terrible name to call them atoms. However, that's the name that has stuck because they've been called that for hundreds of years. Oxidation and reduction are the same way. Here's the history, why they have these terrible names. Reduction comes from the mining and production of pure metals. So when you are digging for something like iron, you don't find just chunks of iron in the ground. You usually find iron ore Ore is a name that sometimes means you have a rock with bits of pure metal in it, but usually means you have some chemical compound with the metal tied into it. So iron oxide is iron ore, which means it's not pure iron. The iron is in a compound, and you have to figure out how to get it out of that compound. And so hundreds of years ago, people figured out if I take iron ore, which is like a reddish rock, and I heat it up really, really high, then it gets lighter and it turns into pure iron. When it got lighter, they were like, hey, I reduced the iron ore into iron. We later learned that this is the chemical equation for it. Iron ore is iron oxide. The charcoal that they were using to heat their furnaces was providing a source of carbon, which they didn't know they were doing. And that allowed the carbon to bond with the oxygen, floating away as CO2 gas. So I was losing mass, and pure iron was left over. But all they knew is I start out with iron ore, I end with lighter iron. So I must have reduced it. And so for hundreds of years, that chemical process has been called reduction because it was getting smaller. Oxidation has a similarly very logical name. This guy named Lavoisier was studying chemical reactions, and he was like, man, oxygen reacts with like so many things. And so every time something reacted with oxygen, he said, let's call that oxidation, which is a great name for things reacting with oxygen. But as we continued to study oxidation, we began to learn that, for instance, if iron reacts with oxygen, it is oxidized to form iron oxide. But we also began to realize that the oxygen was undergoing the same type of change that the iron ore used to undergo, right? And so the oxygen was being reduced. So this is oxidized and that's reduced. And when we go back and study the iron ore thing again, now the iron is being reduced, but the carbon over here is being oxidized because it's reacting with oxygen, although no one quite knew that. And so as we learned more and more about it, we were like, okay, so reduction doesn't actually have to do with something getting smaller. It has to do with something gaining electrons. And oxidation has to do with something losing electrons, which we eventually discovered you don't even need oxygen for. So as of today, it's all about electrons, and reduction and oxidation are terrible names that have nothing to do with what's going on, but they're stuck, and that's what we use. So this is the history. We eventually added the hyphenation when we realized that they are not actually separate processes, but they both always happen at the same time. So redox was born. How do we tell if something is redox? I want to start real simple and broad and look at the better equation of the one that Tyler DeWitt brought up, the more real one with my diatomic chlorine. And we just want to draw pictures of exactly what's going on. So 2Na, what does that mean? 2 sodium atoms. Are they connected to each other in any way? No, the 2 just means I happen to have 2 of them. Do these sodium atoms have a charge?
No.
They don't, because it's pure sodium. They're not involved in an ionic bond, and they're not free-floating ions. If they were free-floating ions, they would be labeled with a plus. Okay, Cl2, what does that mean? 2 chlorines that happen to be connected covalently. Do either of these have a charge? No, because that's not how covalent bonds work. And then 2 NaCl. The way I would draw this is an Na happens to be touching a Cl. But there's 2 of them. And why are they touching each other? Because now their charges attract each other in what kind of bond? An ionic bond where I wish I hadn't done that. I'll just use the purple. Where the sodium is positive and the chlorine is negative. So just from looking at this and using intuition, can we tell if this counts as a redox reaction? Do you have any evidence that electrons moved?
Yes.
Okay, sodium. What happens to sodium's electrons before and after the chemical reaction? Yeah, so sodium used to be neutral, now it's positive, so it must have lost electrons, which is called what? Oxidation is loss, right? So it was oxidized. Chlorine gained electrons, so it must have been reduced. Or you could say chlorine's charge decreased, so it must have reduced. If only it were always this easy, redox would be great.
But there's more.
But there's more. Okay, look at this chemical reaction. Can we tell if this is or is not a redox reaction? So, nitrogen. Are there any charges in my nitrogen?
No.
No. Are there any charges in my hydrogen?
No.
Are there any charges in my ammonia?
No. Yes. Yes.
Well, there's one.
What kind of bond is NH3?
Covalent.
Covalent.
Yeah.
Covalent.
Wait.
No.
It has a pause. It's being. It has a pause for me.
No.
You're looking at ammonia, which is a specific ion.
Is that not this? That's
That's
No,
not
your
all covalent.
ammonium is an ion,
Oh.
NH4. We're looking at ammonia,
Oh.
which is a molecule without a charge.
I see. A molecule without.
Yes.
Neutral.
Yes, so because it is covalent, it has no charge. The nitrogens and the hydrogens have no charge. But we still have to wonder if electrons were forced to change hands in the making of this. And there's only really one way to accomplish that, and it is through a skill called oxidation states or oxidation numbers. Let's rewind a little bit and talk about formal charges. When we taught formal charges, that was the thing where you draw a Lewis structure, you do weird math to every element, and the formal charges that were closest to zero told you that which Lewis structure was the best one. That was what we did there. But in a covalent molecule, the only things we draw Lewis structures for, like that, there are technically no charges. So in real life, formal charges mean nothing. If something has a formal charge of +1, that doesn't mean it is a charged particle. It doesn't mean that it lost an electron. It just means this is a number we assign to this drawing that we made to decide if it's a good drawing or not. Oxidation numbers are exactly the same way. They don't literally mean anything real about the chemicals themselves. They are a tool that we have figured out we can use to determine if electrons have changed in a chemical reaction. So the official definition is the oxidation state of a given atom is the hypothetical, I spelled it wrong, hypothetical charge on one atom if all of its bonds were ionic. And we chose all the words carefully. Definitions are all about putting in words that help make things more clear. So hypothetical is to point out that NH3, nothing actually has a charge, but we're going to say, but if it did have a charge, what would it be? Okay. One atom, the reason we said one atom is because in oxidation numbers, I don't care what all of the hydrogens are doing together. I care what each hydrogen is doing. So an oxidation number is always assigned to a single atom. And then finally, if all of its bonds were ionic, we were just, the way we made the rules for these is we look at things like electronegativity and other more complex things and say, if instead of covalent, this were behaving ionically, which thing would have all of the electrons? Now, as we get into it, this is the part where when you say oil rig, the word electron is really important because when we, instead of looking at electrons, look at oxidation numbers, things work a little bit differently. Here's how oxidation numbers affect our vocab. An atom whose oxidation state increases is said to be oxidizing. An atom whose oxidation state decreases is said to be reducing. So that's the great thing. Most of the time with redox, you will be looking at oxidation states where the vocab just makes sense. Did oxidation go up? Then it oxidized. Did oxidation go down? Then it reduced. So that's the nice part. The vocab just makes sense here. But sometimes, for like actually practical reasons, instead of asking about oxidation state, I have to ask you about electrons. And when you're talking about electrons, the vocab swaps. And that's where oil rig or Leo says ger are important. So if you're using Leo says ger, electrons are built into the mnemonic, so that's great. If you like oil rig better, just make sure in your head, when you say oil, you say oxidation is loss of electrons. Because if I have a loss of oxidation state, that's called reduction. So just be careful with your words, especially at the beginning. Remember, am I talking about oxidation state or am I talking about electrons? Because that changes which words you have to use. You guys get to learn a slightly different method for finding oxidation states than the students last year did, which I think will be easier and faster. Last year, we used a more robust technique that's really good for all the weird edge cases. This year, we were just like, weird edge cases are lame. And so what they did last year was you had to draw a Lewis dot structure, and then you had to do some really specific math to each element, except it was different math than what you do for formal charges. And so it is way, way easy to get those two skills mixed up. This year, we're just going to memorize 4 rules. And if you know the 4 rules, you should be able to get all of the oxidation numbers that we need. So what we're going to do is we're going to walk through them one at a time and apply the rules to our covalent reaction up top and see if we can determine, is this oxidation or is it not? So rule number 1, a pure element always has an oxidation state of 0. And I think I've said this before, the reason why I put crosses through my zeros in chemistry is because if I didn't, you might think that it always has an oxidation state of oxygen, which is confusing.
You could write out 0.
I could, but this is faster.
That was like lazy.
Iron, Fe, is it a pure element?
Yes.
Yes, there's only iron in it. Oxygen, O2, is it a pure element? Yes, because there's only oxygen in it. S8, is it a pure element? Yes, because there's only sulfur in it. So this one is easy. It's an easy rule for you to forget, but anytime you only have one element in a particle, then it is an oxidation state of 0. And if we go back to the definition, we're asking if it were ionic, who would be taking the electrons. So if the bond between 2 oxygens happened to be an ionic bond, then we have to say, okay, which one is stronger? And the answer is neither, because they're both oxygen. So that means neither of them could gain a charge. And so it must have an oxidation state of 0. Scrolling back up, can we assign oxidation numbers only based on rule 1 to any of the atoms? Like what? The first nitrogen is pure, right? So it has an oxidation number of 0.
Isn't the second one 0 too?
Which one?
Like
Yeah, hydrogen is only hydrogen, so it is 0. Is NH3 a pure element? No, so we need more rules. Rule number 2. An ion's oxidation state always matches its charge. Remember, the definition is hypothetical charge if it were ionic. That means if it is ionic, then it's just literally the charge. There is no hypothetical here. So the sodium ion has what charge?
1.
Positive 1. Therefore, it has an oxidation number of positive 1. Chlorine ions have what charge?
-1.
Negative 1. Magnesium ions have what charge? All right, and then there's one, I need to make a note to add this. Let's do a compound. So if I did like BeF2, is this covalent or ionic?
Where's B?
BeF2.
Oh yeah. Ionic.
It's ionic. Ionic means it's made out of ions. The definition of ions is charged particles. So if I have ions, I look up the charges. What is the charge of beryllium?
+2.
Plus 2. What is the charge of each fluorine?
-1.
-1. And that goes to our other part of the definition. An oxidation state is the hypothetical charge of one atom. And so, yes, I have 2 fluorines here. I don't want to write -2. I would rather write -1, or if I really need to write it all, I would write -1 2 times, because each fluorine has a number of -1. And that's way more important than knowing what all of the fluorines are doing. I need to know that one fluorine is -1. Do I have any ions in our example? No, I don't. So that actually doesn't help us at all. So we need rule number 3.
Wait, what would be the charge? Yep.
What would be what?
What would be the oxidation of
0.
The BE is +2, and each F is -1.
Okay, so you just weigh them like individual.
So it does not have one? Or would it just be 0?
No, BeF2 is a compound. Oxidation states apply to one atom. And so this atom, beryllium, has an oxidation state of +2.
Okay.
This atom has an oxidation state of -1. There happens to be 2 of them. So each fluorine has an oxidation state of -1.
But you would write -1 if it like.
Yeah, the way we normally work with it, and you'll see, is you would write your answer the way I just have, where you just notate near the beryllium +2 and you notate near the fluorine -1. Almost always, if I have more than one of something in a compound, they will all be doing the same thing. They only start branching into weirdness when you get into giant organic molecules, which we mostly don't look at in first year chemistry. So both fluorines are doing the same thing, so I only have to write the number once, because I'm just saying, hey, if you get a fluorine out of this molecule, it's going to have a -1. All right, rule number 3. This one is there are, ooh, look at that, it disappeared. There are 3 elements that you just need to remember what number goes with them. And one of them has an exception. If you see oxygen in a molecule, it should have an oxidation state of -2. The only exceptions would be if the type of molecule is a peroxide. It's like there's a whole family of molecules called peroxides. The only one that we care about is hydrogen peroxide. So effectively, if you see oxygen, it's -2, unless you're looking at H2O2, and then the oxygen is -1 instead. Bye, friends. If you see hydrogen, it is always +1. There are super weird cases where it can go to -1, but you will not see them. If you go to college or whatever and you see hydrogen with a -1, you're not allowed to say that I lied to you, because I just told you it happens sometimes, but it won't happen here.
So we should just ignore that.
Hydrogen is +1, always. And when I say always, I mean here it is always +1. When you go to college, it might be -1 sometimes in weird cases. But for us, +1.
Well, things like that I'll probably forget.
Yeah, I don't like saying things that are totally going to work for my classroom but aren't actually true.
There are only a couple things that you've said without like conditions.
I know.
Just don't say don't question the conditions.
Everything has a but. Hey, wait, here's one. Here's one. Fluorine is always -1.
Really? For real?
Yeah.
No cap. But it's an exception to the oxidation fee.
It's the exception that proves the rule.
Yeah.
Okay, if you know those 3 things, maybe we can do more. Let's go up. Can I assign any more numbers?
H.
H is always
1.
+1. So we can put a +1. Do I know anything about N? Nope. So I need rule number 4. Rule number 4 is the sum of all of the oxidation numbers in a compound must equal its charge. A lot like formal charges did. So now for the last rule, we're going to do the same notation that Tyler DeWitt does because it's compact and I like it. What is the total charge of NH3? Is it an ion or is it neutral? With a compound, you always know it's an ion if I wrote the charge.
Neutral.
So it must be neutral. So what we're going to do is we're going to say each hydrogen is +1. Therefore, altogether, they are +3. When I add all the numbers together, it needs to equal 0. So then we do a simple math problem. What +3 equals 0? -3. That means my nitrogen must be -3. And we have officially assigned all of the oxidation numbers. So now we look at, is this redox or not? Nitrogen started out at 0 and ended at -3. Hydrogen started out at 0 and ended at +1. So, did the oxidation numbers change? So it was redox. Which element was oxidized?
Hydrogen.
Hydrogen was oxidized because its oxidation state increased. Nitrogen reduced because its oxidation state went down. So if we're looking at oxidation states, the vocab just makes sense. Only when we talk about electrons does it flip. And one way you might think about that is electrons have a -1 charge. Things tend to flip when you multiply by -1. So if you want to use the word electron to multiply your vocabulary by -1 so that it flips, it's not a great analogy. All right, let's practice a whole bunch of these. Go back. I can't. I did. Why? Okay. This is not NH3 is not an ionic substance. So in real life, nothing has a charge.
Okay.
We need to assign oxidation states, which are hypothetical charges. And hypothetical charges have different rules than real charges. So the way we figure out nitrogen is the hydrogen always gets a +1, and the total of all of the oxidation numbers has to equal 0. So if those three are all +1, that 1 has to be a -3. Now, it happens to match that nitrogen would usually have a -3 charge in an ionic compound, but that's not always going to be how oxidation states work. You can get weird, +5s and stuff with oxidation states.
Wait, so do we not do anything like the coefficient?
Correct. We're looking at one atom at a time. The coefficient just means we happen to have multiple copies of that one atom. Yes?
So what if there was an H3 in that problem and we didn't happen to know anything?
Rather than doing what ifs, let's do 8 more examples of assigning oxidation states and see if it answers all our questions. 03. Let's just walk through our rules one at a time. Rule number 1, is this a pure element?
Yes.
Yes, so its oxidation number is 0 and we're done. Yay! Na2S, sodium sulfate. Rule number 1, is this a pure element?
Nope.
No. Rule number 2, is this ionic?
No.
Well,
Oh, say no. Yes.
No,
I
it's
have a
not.
metal plus a non-metal,
Oh,
which
ionic.
makes it ionic. That means it's made out of ions. So the rule is I use the charge of the ions. What is the charge of sodium?
+1.
No, +1.
+1. And what is the charge of sulfur in an ionic compound? -2. If you wanted to double check that this is following rule 4 and everything adds up to equal 0, you could recognize that 2 sodiums and 1 sulfur, where the sodiums are +1 and the sulfur is -2. If I add all those together, do I get 0? Yes, so this all works. All right, is H2O a pure element?
If that was an A2S, would you just write the charges above it and that would be the answer?
Yes,
Yeah,
so
even-
the answer, if I'm asking you oxidation numbers, the answer is +1 and -2. Sodium is +1, sulfur is -2. H2O, is it a pure element?
Nope.
Is it ionic?
No.
No, so now we look at rule number 3. Does it have any elements that we memorized?
Yes.
Yeah, hydrogen is always,
+1.
oxygen is always.
Negative.
If I were to add up all the numbers, would it be 0? Yeah, it looks just like Na2S, where the 2 hydrogens and the oxygen cancel out.
So it always has to be 0?
No, it always has to match the total charge of the compound, which is usually 0.
If it was like H2O and then it had like a -1.
Let's do 5 more examples and see if it answers your question. CH4. Not pure, not ionic. Does it have any elements that we memorized?
Yes.
Yes, but carbon isn't one of them. So now we do the little notation math thing. The answer for hydrogen is +1. I happen to have 4 hydrogens, so that's a total of +4. Because CH4 is a neutral compound, all my numbers need to add up to equal 0. -4 + 4 = 0. So this carbon needs to have an answer, an oxidation number of -4.
And it does.
And it sure does. Remember, this is not a charge, this is not made out of ions. Carbon doesn't have a charge of -4 because it doesn't have a charge at all. It has an oxidation state of -4, which is a slightly different reality. Hey, look, this reminds me of the question you asked. Okay, where do I want to start? Can I assign any numbers right away?
No. It's covalent.
Oxygen is always -2. I happen to have 4 oxygens, so that's -8. If I add all of them together, what does it need to equal? -2. The sum always needs to match the charge of the particle. Because this one is a polyatomic ion, the charge of the particle is -2. So what minus 8 equals -2?
6.
+6. My sulfur has a +6. And this is also a demonstration of why you can't just look at the periodic table. The sulfur ion has a -2 charge. Sulfur in this compound has an oxidation state of +6, which is not -2.
So why did you find the oxygen before the sulfur?
Because we know that oxygen is always -2. And we use that knowledge to math our way to knowing what sulfur must be. Yep.
So does that mean that we should look at the periodic table? Oh, this is +4, this is
Yeah, only look at the periodic table if you have ions. If it is ionic, the periodic table tells you the answer. If it's covalent, you got to go another route. C2H6. Do I know anything at the beginning? Hydrogen is always +1. I happen to have 6 of them. What does it need to sum to equal? 0 in this case. So what +6 = 0? -6. Now, I happen to have 2 carbons, so I need to divide by 2. Each carbon is, oh, my +1 looks weird. Each carbon is -3. Remember, the part of the definition that matters here is the oxidation state applies to one atom. And so, yeah, all of my carbons are -6, but I care about each carbon. And that's important because in some cases, you'll see it at least a couple of times. It's possible for C2H6 to have a chemical reaction where some of the carbons go to one compound and some of them go to a different one. You've seen stuff like that before, like when balancing. And so it's possible for one of those 2 carbons to, for instance, reduce while the other one stays the same. And so that's why we're tracking each atom, because it could do more than one thing. Do I have 1 or 2 more? 2 more. Okay. Sodium carbonate. Is this ionic or covalent?
Ionic.
Ionic-ish. Ionic means I have a positive. Let's do green for positive. I have a positive and a negative ion. But because the negative ion is polyatomic, that one is going to behave covalent. Okay? And so effectively, we need to redo the SO4 work, but only for the CO3 thing. I'm making it sound hard. It's really easy. Sodium is an ion. What is the charge of sodium?
+1.
+1, so we're done there. Oxygen is always -2. I happen to have 3 oxygens, so that's -6. I have 1 sodium, so that's +1. Is this total compound neutral? Yes, so it will add to 0. 1 minus 6 plus what equals 0? So plus 5 goes right here. And so this would be a positive 5. Yep. So it's really not that bad. It's just recognizing if you just begin at ionic, you might be tempted to try to look up the charge of carbon, but that it can't be done here because the carbon is tied into that polyatomic thing, so you have to make sure they all add up to equal 0. Last one. Hydrogen is always what? Plus 1. Oxygen is always what?
Non-negative 2 here.
Usually it's minus 2, but this time it's minus 1 because hydrogen peroxide is different. Remember that you can always use rule number 4 as a way to check your work. If you did it wrong, then when I try to add all of them together, plus 2 minus 4 does not equal 0. So you go, oh, maybe I forgot that it's supposed to be minus 1 for hydrogen peroxide. Okay, so that was a lot of good practice. How do you apply it? Well, I accidentally put the same problem in here twice, so I'm going to do this really rapidly because we've done it together. Nitrogen is pure. Hydrogen is pure. NH3, I would do plus 3, plus 6 is 0, minus 6, minus 6. Nope, I'm doing wrong math. Plus 3, no, stop.
Just cross it out.
Plus 1 minus 3. Okay, in this case, which one is being oxidized? Hydrogen is oxidized because you see its number increase, and nitrogen is reduced because you see its number decrease.
So if it's positive or negative, that'll tell you
How
which
do you know that
one's
nitrogen
negative.
is negative?
If it's reducing, it is decreasing. That doesn't necessarily mean it is negative.
Oh.
What matters is, did it decrease from left to right? So if we were to write it more clearly, we would say nitrogen goes from 0 to negative 3, which is a reduction. Hydrogen goes from 0 to positive 1, which is an oxidation. Mg is, what is the oxidation state for just magnesium?
0.
0 because it's pure. What about oxygen gas? 0. What about magnesium oxide?
Not pure.
Not pure. Is it ionic? Yes, so I can look up the charges on the periodic table. Magnesium is?
Plus 2.
Plus 2. And oxygen is? Minus 2. Now, the other way you could have done this is, even with ionic things, the rule for oxygen is that it's always negative 2 unless it's pure. So you also could have just been like, oh, look, oxygen, negative 2. That means magnesium has to be positive 2. If my magnesium goes from 0 to positive 2, what has happened to it? It has oxidized. If oxygen goes from 0 to negative 2, then it has reduced. Doing okay? So when we, to answer your question, way up here, the 2 only matters because it's describing reality a little bit better. I happen to have 2 sodiums, but when I'm asking what's happening to sodium in this reaction, this sodium becomes positively charged, so it lost an electron, oxidation, so it oxidized. This sodium also oxidized. Because most of the time everything does the same thing, we just will sort of say, hey, the sodiums oxidize. And we don't need to know that it happens to be 2 of them doing it. All right, 2 more. What's my oxidation number for Fe?
0.
And O2?
0.
And Fe2O3?
Not 0.
We don't know yet.
So we got
Well, it is 0, but we need to
Oh,
like do the
F
thing.
is a transition metal.
Right? But do we know anything about oxygen?
Yes,
Yeah.
-2.
Oxygen is definitely -2. I happen to have 3 of them, and it needs to equal 0. So +6 minus 6 equals 0. What is each iron?
3.
+3. And then we identify, I could just ask you the question, hey, is this a redox reaction or not?
Yes.
Yes, because any of the numbers changed during the reaction. That's not iron. Iron goes from 0 to +3, so what happened to it?
Oxidized.
And oxygen goes from 0 to -2, so it reduced. Last one. Zinc.
0. Ooh, she's beefy.
What? Oh, because it's bigger?
Yeah.
HCl. What do I know about HCl?
It is not covalent.
It's covalent.
And it's not 0, but H is
But we know what
+1.
Hydrogen is +1, so chlorine has to be -1. Now, if I look at zinc chloride, what do we know?
Zinc is
It's ionic. It's ionic, so we can look up the charges. I don't know the charge of zinc. Zinc is a transition metal. But we do know the charge of chlorine,
-1.
-1. If my 2 chlorines are -1, my zinc has to be +2, and my hydrogen 0. So zinc goes from 0 to +2, so it oxidized. Hydrogen goes from +1 to 0, so it reduced. Chlorine goes from -1 to what? So what about chlorine?
It stayed the
Does it just
same.
not do anything? It says neutral. It's not redox.
You guys, I planned this lesson so well
Oh.
because we're going to talk about chlorine next. No. Is this a redox reaction?
No.
Did any of the oxidation numbers change?
Yes.
Yes. Some things are oxidized, some things reduced. So this is a redox reaction. Next section. Why do you keep doing this? Because I'm recording and it makes the computer mad.
I do that. That happens to me all the time.
Do you have a lot of stuff running in the background?
No.
I do.
My computer's
My computer's super hot right now. Balancing redox reactions. In the last example, notice that chlorine didn't actually change. It started out with -1, it ended with -1. Anytime an ion doesn't change like that, it has a special name. It's called a spectator ion. What do spectators do
Stay the same.
in sports stadiums?
Oh, sorry. They
They just watch. So this is actually a really special thing about redox reactions. There are some chemical reactions where you must have exactly this chemical and exactly that chemical to get what you want out of it. With redox reactions, you must have the thing that is oxidizing and the thing that's reducing, but the spectator ion doesn't matter. So if I wanted this particular zinc hydrogen reaction to occur, then I need zinc and I need something that will give me hydrogen. Zinc chloride or hydrogen chloride will give me hydrogen, but I could also do HBr or H2S or lots of things. The spectator ion doesn't matter. The same chemical reaction will occur no matter what the spectator is because the spectator isn't doing anything except for watching. Which means when we write redox reactions, we will sometimes write them like this, where if I'm reading this out loud, I would say aluminum reacts with a source of copper ions, like copper sulfate or copper chloride or something, who cares? And you get a source of aluminum ions and pure copper. So they just don't even write the spectator ion at all because it doesn't matter what the spectator ion is. That is helpful for me being able to go into the closet and just grab something that is a copper compound, knowing that it will work, but it's unhelpful when it comes to balancing. Are the number of atoms currently balanced in this? How many aluminum atoms do you see on the left? How many aluminum atoms do you see on the right? One, it just happens to have a charge. Copper's on the left, copper's on the right. Yes, it is balanced, but are the number of electrons balanced in this equation? What charge can you identify on the left? +2, left. What charge do you identify on the right? So no, the electrons aren't balanced. The problem with hiding the spectator ions is it looks balanced, but it's not. So we have to learn a thing that's gonna look weird, and Nina's gonna complain about it. But after we do it a couple of times, you will begin to see that it's basically the same.
So it's like balancing the equations but with electrons?
Yes. Okay, we're going to do what's called the half reaction method, and this ties in that last thing that you learned from Tyler DeWitt where you're adding electrons into things. Here we go, adding electrons in. First, let's assign some oxidation numbers. Pure aluminum has what?
0.
Copper ion has what?
0.
Copper ion
Oh, sorry, +2.
+2. Aluminum ion?
+3.
Copper pure?
0.
All right, I want to split it between oxidation and reduction. Which element is being oxidized?
Aluminum.
Okay, so the way we're going to write the aluminum half reaction is by writing the stuff that we know about aluminum. For instance, it starts out as pure aluminum, and it ends as the aluminum 3+ ion. Step 1 is done for aluminum. Copper is being reduced. We know that it starts out as the copper 2+ ion, and it ends as pure copper. Step 1 is done for copper. So all we've done is extract my oxidation and reduction halves so that we can work on them individually. Right here, the last sentence of step 1 says balance by number if necessary. We've already identified that they're balanced by number. I have one of each thing, so there's none of that work to do here. Step 2 says...
If they weren't balanced, you would have to balance the equation first to continue.
We'll see that down here. I was careful. Step 2 says add electrons to show oxidation or reduction. So this is the thing that Tyler DeWitt did to make the charges balance. I like to write a little math problem. So the total charge of pure aluminum is 0. The total charge of my aluminum ion is +3. 0 does not equal +3. The only thing I'm allowed to do is put in negative numbers because it's electrons. So where do I put a negative number to make this true? Heidi says if I put a -3 right here, then it will become a true statement. So how would this be reflected with chemicals? My aluminum stays the same, my aluminum ion stays the same, but I'm also including 3 electrons. That's where we can get a -3. Now what's nice is if you always set it up like this with oxidation and reduction, oxidation is what of electrons? Oxidation is oil. Oxidation is loss. So when you're doing a half reaction for oxidation, you will always start with a whole thing and then lose electrons. Okay? Reduction is gain. You're always going to start with some electrons and then stick them on. So we know in advance that because it's reduction, the electrons are going to need to go on the left side, but let's do all of the work anyway. Copper has a +2 charge. The pure copper has a 0 charge. I'm only allowed to add negative numbers, so how do I make this a true statement? Put a -2 over here. If I reflect this with chemicals, 2 electrons plus my copper ion will become pure copper. If you practice this exactly the way we're doing it in the notes, Oxidation always has your electrons on the right, and reduction always has your electrons on the left. It's always going to work that way, so you can just like do it. Now, what matters is these are supposed to be two halves of the same whole, and the numbers of electrons don't match. So step 3 is we need to multiply each half by whatever we need to multiply it by to make those electrons match. If I multiply everything by 2, I'll have 6 electrons on one side and 4 on the other. So we look for common multiple.
Oh no.
If I multiply this side by 2,
No.
and I multiply this side by 3, will my electrons match? Yeah, my electrons will match. So let's rewrite it. 2 aluminums becomes 2 aluminum ions plus 6 electrons. What time is class over?
12:20.
Okay, we're going to finish early. You guys are doing great.
Oh my god, I really don't feel like it.
We only have one example after this.
I'm trying out this. It's almost done.
All right, on the right side, 6 electrons plus 3 copper ions yields 3 copper atoms. So in step 1, we made sure that it was balanced by number. In step 3, we are making sure that they are balanced by charge, where all the electrons match. And now we're technically done balancing. All we need to do is put it back together. Step 4 is to recombine. And the way we do that is if something is on the left side of its arrow, it needs to go on the left side of the new arrow. If something is on the right side of its arrow, it goes on the right. I like to underline as I write because then I don't lose things. So that 2Al is on the left, so I'm going to write it on the left. This half reaction doesn't have anything else on the left, so I'll go check on copper. I have 6 electrons plus 6 electrons and 3 copper ions plus 3 Cu2 plus yields 2 aluminum ions, 2Al3 plus 6 electrons plus 3 copper atoms. And now we're done-ish. We've actually done a little bit more work than we had to do. And I'm going to show you a crazy complicated algebra problem. The square root of 2xy plus 4 equals y squared plus 4. What's the first thing you'll do to solve this?
Hold on. Let me just write it down.
Just get rid of the 4, right? I can subtract 4 from both sides and they go away. All that other nonsense I wrote was not important.
Of course not.
If something is written on both sides of an equation, then we don't need it. Is there anything I can cancel out from my chemistry equation? The electrons. So the official correct final answer is 2Al plus 3. No. I just troll my students sometimes.
No.
Did I show you guys the Boom Dave video? Boom Dave!
Yes.
That was a B-Day special. My A-Day students didn't get that.
Wait, so
Yay.
I'm confused. So is this basically saying that the example Al plus Cu2 is wrong?
At the very top?
Yeah.
Yes.
Oh.
Because what's actually going on is you have something like Al plus CuCl2 forms AlCl3 plus copper. And what they did is before they balanced it, they erased the chlorine because it's a spectator ion and said, now figure out how to balance it. And so this is the correct balance because 2 aluminums will combine with 3 copper ions to form 2 aluminum ions plus 3 coppers. But this will only happen if you have some spectator ion that you just find in the closet.
Okay.
It just doesn't matter what the spectator ion is. It could be chlorine, it could be carbonate, it could be sulfate, it could be iodine, it could be anything. Carolyn.
So I'm still
between like the oxidation when we said something oxidized when we used the charge that we made, and then when we said something oxidized because the electrons changed? Are they the same, like oxidized?
They're just different ways of talking about the same scenario. So aluminum is oxidizing because its oxidation state is going up. But how do I get a positive charge? Something becomes positive by losing its electrons, right? So if I'm talking about oxidation, then oxidation goes up, therefore it oxidized, like oxidation numbers. If I'm talking about electrons, that aluminum lost electrons. Oxidation is loss of electrons. And so you just have to make sure if you're talking about electrons, the vocab sort of swaps, but it's still the same scenario, you just describe it differently. We have one last example. I just want to balance one more thing with you, and then we're done for the weekend.
Forever. Just forever.
Not forever. We have a whole unit after this where we get to play with acids.
Great.
Okay.
Yeah.
We're going to walk through the whole thing together again. It's almost identical, but we'll be able to go just a little bit faster because we've seen it all work. So the reason why we need to identify oxidation and reduction is because then it will fit the pattern and we'll know for sure that like the electrons go on the right or the left. You can still balance it this way without knowing which one is oxidizing, but I like to identify.
On the test, are you gonna have these steps or just?
No, you'll have to know them. On your homework, I don't have the steps written out. Copper is +2 because it's an ion. Iodine is -1 because it's an ion. Copper is +1 at the end. Iodine is 0 at the end. So, which one is oxidizing? It has an increase in oxidation state. Iodine goes from -1 to 0. So if I were to write the half reaction, I would say iodine ions become I2. And for reduction, copper ions become slightly less positive copper ions. That should be a 1. Now, the last sentence of step 1 says balance by number if necessary. Is that necessary here?
Yeah.
Because iodine looks weird. We fix this the way we've always fixed it. If I have an iodine molecule, that means I need 2 iodines to make it possible. This doesn't come up a ton, but when it does come up, it'll look like this, where you have a diatomic molecule, and so you add a 2 to make it all happy. So let's write up our charges so we know how many electrons to add in. What's the total charge of my iodine ions? -2 equals 0. That's not true. Where do I add negative numbers? On the right side. So I copy down my iodine information and I add how many electrons? 2 electrons. For copper, it starts out at +2, it ends at +1. I'm only allowed to add negative numbers.
So plus electron.
So there's 1 over there on the left. So that means 1 electron plus my copper ion will become my different copper ion. So we've finished step 2. On step 3, multiply the half reactions as necessary so that the electron numbers match. How do I make 2 and 1 match each other? Multiply the right one only by 2. So like when you're doing this on your homework, you're not going to rewrite the equation nearly as many times because you can just add to what you already have written. But we like to carefully break it down in the notes, so I'm going to rewrite it again. 2i becomes I2 plus 2 electrons 2 electrons plus 2 copper 2 ions becomes 2 copper 1 ions. Now, because one of them has 2 electrons on the right and the other one has 2 electrons on the left, we already know in advance that they're going to cancel out. So rather than writing it all out and then just crossing it out, let's just skip it. To combine these into our final answer, I can say 2 iodine ions will combine with, don't care about the electrons, 2 copper ions to form I2, don't care about the electrons, plus 2 copper 1 ions.
So is this like really the way we should have been balancing equations the whole time?
No, this only applies when people take away information from the chemical equation. We only have to do this because there are components of this recipe that were left out intentionally. You can't actually get a bottle of Cu2+. Because positive ions would repel one another, it doesn't work. But you can get a bottle of CuS, copper sulfate, which is a source of Cu2S, or 2+. And when I combine it with iodine, the sulfate doesn't do anything, it's just a spectator. And so they didn't include the spectator in this recipe because instead of using copper sulfate, you might choose to use copper 2 chloride, because that's also a source of Cu2+.
Okay.
And so this is more of a generalized equation that says you can use any source of copper ions because the spectator ion doesn't matter. Okay. But when they write it generally like that, it makes it weird to balance.
Okay, got it.
The very last thing to mention, because I'm not sure I mentioned it, is way back at the top when we were learning the 4 rules for oxidation numbers. If you did want to learn the Lewis structure version of it, where instead of memorizing any of those rules, you just draw Lewis structures and do a little bit of math, there's a link, right? Where's the link?
I see it. It's there.
Well, there's a link in there. There it is. Lewis structure method. That's just me spending like 6 minutes showing you how we did it last year. It'll totally work, but I think this other way is faster, and it's also the way Tyler DeWitt does it, and he's cool. So that's just, if you want to learn other ways to do it, go watch the video and you can learn them, and I can help you with it if you care. Any final questions? No? No? All right, lesson over. Stop recording.